Hello mathematicians, we're now going to have a look at the reverse chain rule. Now this is a really good example of a topic where you can be baffled by I was going to say bullshit, but of course that'd be wrong to say that. So you can be baffled by the terminology, or you can get your head around it and then forget the terminology and work with the key understanding, the key idea. So the reverse chain rule, sometimes called integration by the method of substitution, and we'll do a fair bit more on that. But for the moment we're doing it very formally. So you know about the chain rule, or the function of a function rule, which has been used to differentiate composite functions. So if we had a function y equals f of u, and u itself was some function of x, so we've got that y is some function of a function of x, then we can use the chain rule. We can say that dy dx is dy du times du dx. And if we can do that, it should be possible to integrate by undifferentiating. So you run the chain rule in reverse. So in other words, since dy dx is f dashed of g of x, which we would have said is f dashed of u on our problem sheet, g dashed of x, then if we take the integral of both sides, so we integrate this, which is written like that, and so we integrate this, and I've mixed up the f there, that should be f dashed with a capital F, then we get back to the original function. Now that all sounds very confusing, and I'm using a slight variation on the symbols in the textbook, and I'm doing that to try and make it compatible with the reference sheet. But the thing is that it doesn't really matter about the terminology if we get the concept behind it. And I'm hoping that we will once we start working some examples. But here is the key bit. The secret to using this method for integration is to recognize when a function has this form just here. In other words, you look at what it is that you're integrating, you realize that there are two parts to the thing that you're integrating, and one of those parts is related to the differential of the other. And then what we do is to use a substitution. Now I know it still sounds like I'm talking mumbo jumbo at this stage, but this is a key concept. So if I can just repeat it so that we can come back to it, when we go to apply this method, even if it says use the method of substitution, this is what we have to recognize, that the integral that we're dealing with will have two parts to it, one of which is related to the differential of the other. So in essence, it's just again looking for patterns. Remember in the product rule for differentiation, we had to recognize that there were two parts multiplied together. Well, it's a similar thing here. We look at the integral, we have to recognize that there are two parts being multiplied together. But when we're going to use this substitution technique, one of those parts has to be related to the differential of the other. We'll see in a little while what related means. So, for example, and I hope this is where it will become clearer, if we wanted to find the integral of this, well, I guess we've got the option of expanding out this cube, multiplying everything through by 8x, and doing it term by term. So that is an option. It's a fallback position. But if this was to the 11th or the 12th power, that would become pretty well untenable. But what we do notice is that we've got two parts to this integral. We've got this part and we've got this part. And if we think about it, we can see that this part, 8x, is related to the differential of this part, because the differential of this part, x squared plus 3, is of course just 2x. So we make this substitution. Now this is pretty sophisticated level of mathematical thinking in a way, but it will become commonplace to you. So we let u equal x squared plus 3. We let u be this thing here, which we are taking a function of. So if u is x squared plus 3, then what we're doing to the u is that we're then cubing it. So we're taking a function of a function. So if u is x squared plus 3, then du dx, so this is our next step, is 2x, and 8x is of course related to the differential, because 8x is clearly just 4 times 2x. So once we've done du dx equals 2x, we then split it up. We basically separate this fraction. So du is clearly 2x dx. So when we go to rewrite our integral, we're going to replace this part with u. We're going to replace 8x with 4 times 2x. But 2x dx go together and become du. So you might need to take a moment to get your head around that, but this is the key step. So 8x x squared plus 3 dx becomes 4 lots of u cubed du. Now that then becomes just an easy integral. U cubed integrates to u4 on 4. That 4 cancels just there, so we're just left with u4 plus our constant of integration. So then our last step is to change the variable back again. So where we had u, we replace it with what it was, x squared plus 3, so that was our integral. Now, let's have a go at this example out of the textbook, which in a way probably helps you through a little bit too much, I think. So we want to find the differential of the square root of 2x squared plus 3, so a question just like on your exam paper. Hence find the integral of 2x on the square root of 2x squared plus 3. So this is a common sort of question. It could even come up on a 2-unit paper as a hard question where they guide you through it, or it could come up as just B part 1, just doing this bit, and they might tell you the substitution to use. So let's look at it. So first part is pretty straightforward, relatively straightforward. We want the differential of the square root of 2x squared plus 3. So we first of all rewrite that without the third sign. So we want the differential of this thing. Then we do the differential. So that is a half of 2x squared plus 3 to the minus a half. And when we rewrite that back in third form, times 2x, so that's the first bit of our function of a function rule. We differentiate what's in the brackets, which is 2x. And then this is our final answer, that the differential of the square root of 2x squared plus 3 is 2x on the square root of 2x squared plus 3. Now because in any maths question we're always scanning to look for patterns, similarities, close relationships, then of course we recognise this bit here as what they want us to integrate just here. So now we know the answer. If we integrate this, then we're integrating this, and the integral and the differential cancel each other out. So that second part is almost trivial after that. The integral of 2x on 2x squared plus 3 is the integral of the differential of that, which of course is that. Now you notice that we're not putting in constants of integration here. It's a sort of a special exemption for these sort of questions because we knew what we started with. So it's not like we're wondering what we differentiated to begin with. We knew exactly what we differentiated. So have a go at these questions in 11H, 7 to 10. Try 11A just for fun. But before you start your exercises, think about this. Out of all of that rigmarole that we've just looked at, what really was the big idea? And the big idea was, in a nutshell, that if we have differentiated something using the function of a function rule or the chain rule, then we can undifferentiate and get back to the original function. And also, if we're just given a function and we can see that it's got two parts in it, one part of which is related to the differential of the other, we should be able to do the reverse chain rule to find the integral using the method of substitution.